So far, what we saw was we saw how to calculate the running time of the insertion sort algorithm, and then we also saw how to calculate the running time of the merge sort algorithm, right? Um, what we are concerned about is what happens when, as the size of the input increases, how does the running time of the algorithm change? If my n increases to something very large, or as n starts to increase, or as n starts to decrease, how does the behavior of the algorithm in terms of speed change? So that is exactly what is known as studying the asymptotic efficiency of the algorithm, and this is exactly what we would like to do. We say that an algorithm is asymptotically efficient if its running time does not worsen terribly as the number of inputs become very large. So when choosing an algorithm, what we would like to do is choose an algorithm that is asymptotically efficient. That is, um, it is very likely that usually when we have problems, our number of size input may continue to grow, right? So whenever we have a choice, we always want to choose an algorithm that is asymptotically more efficient. So there are three commonly used methods or ways to calculate asymptotic efficiency. The first one is the big theta. So to calculate big theta of an algorithm, what we want to see is that the algorithm does not have a really extreme worst case and best case. An example is the merge sort algorithm. So formally, we say that any algorithm that has running time fn, right? Say, for example, in the case of merge sort, our fn would look something like this. We say that the function fn belongs to big theta of another function, another running time, which is a shorter or more abbreviated running time, if there exists two constants, C1 and C2, such that our function fn can be sandwiched in between the C1 gn and C2 gn. So in other words, in the case of merge sort, what we know is since the dn is a relatively very small number compared to n log n, we can simply ignore it. And then we can also ignore it because we know that in the case of merge sort, no matter what happens, this part is always executed. That is, the running time is always at least n log n, and at most a very high big constant c, n log n, and then plus some terms plus some constant times n. In other words, such a running time can be expressed as um, being in between a very small constant times n log n to a very large constant times n log n. So we based on the behavior of the merge sort algorithm, which we know that the worst case runtime is also always some constant times n log n, it can easily be sandwiched between C1 times n log n and C2 times n log n. So hence we can say that the running time of a merge sort algorithm is big theta of n log n. We can skip this part because this is a relatively much smaller quantity compared to n log n. So we also typically say that merge sort running time is big theta of n log n. And what theta does is, what big theta does is it gives us a running time where we know that the algorithm does not run faster than n log n or does not run slower than n log n. So it gives a tight bound for the running time. So it is also considered an asymptotically tight bound definition for our function fn with running time fn. So once again, what big theta tells us is big theta of a function, big theta of a function is a running time that is going to be some constant times that running time, maybe in the best case, also some other constant times that function in the worst case. In other words, it'll always be around n log n. Now, something that's very interesting and quite important to note as well is that say, for example, our function's running time, Fn, has this characteristic, right? Maybe at the beginning, when let's say n equals 1, 2, 3, and 4, the running time stays constant, goes down, and then goes back up. And then after n equals 5, it shows a sort of uniform or more predictable behavior, right? So typically, for the case of doing asymptotic analysis, um, we usually ignore the up to n naught where we don't see a predictable behavior of a function, right? Let me discuss an example. Say we have two running times, n square and n factorial, right? If we have these two running times, we see that as n increases, the running time will become, for n equals 1, this will be 1, right? For n equals 2, this will be 4. For n equals 3, this is going to be 9. Now with n factorial, when n equals 1, this will be 1. When n equals 2, this will be 2. When n equals 3, this will be 6. It seems that the factorial function is growing much slowly compared to the n square function, right? But this may not be the case as we continue to increase the numbers, right? The factorial function may grow faster or slower or even much slower than what we see up to n equals 3 or n equals 4. So for that reason, what we do is we intentionally skip everything below a certain n naught. That is, for a certain value of n up to that point, we ignore the behavior of the algorithm. We totally skip it. And then we look at the part of the trend that is more predictable or more like representative of the nature of the speed of the function. So formally, we say that the running time of an algorithm is big theta of gn if for our input function fn, there exists positive constant c1 and c2, and also some constant n naught, such that after n naught, that is when n is more than or equals to n naught, our running time can be sandwiched between C1 times this big theta of Gn, so sorry, our big theta function Gn and C2 times the same big theta function. The next asymptotic notation is the big O. It is also quite commonly used. Now, what big O does, it gives us the upper bound. That is, with big O, we are focused on what is the worst case scenario for this algorithm to run? That is, what is the maximum, how maximum inefficient can the algorithm be? So in the case of insertion sort, we know that the running time is an squared plus bn plus c, right? In this case, we know that for a really, really good set of inputs, insertion sort may not need actually any square time, right? That is, when things are already sorted, insertion sort may effectively run in approximately, let's say, constant a times n in running time. But what BIGO does, it explicitly asks, what is the upper bound for the function? That is, if my data was the worst case scenario for the input, what would be the running time? So in that case, we clearly see that out of these three terms, the term that can take the largest value is an squared. So we say that the running time of insertion short is big O of n squared, because this running time translates into big O of n squared. This is the maximum or the worst case scenario in which the algorithm could run. So once again, what we have to carefully check is that we want to look for the behavior of the function, not for some smaller values of n, where the behavior of the function may not be representative of the asymptotic trend of the function. For example, like for this particular function fn, this particular running time, you see that for maybe certain value of n, it goes down and then goes back up and then comes back down and then becomes stable. So formally, we say that big O of a function's big O is running time is big O of Gn if for that function Fn, for that function's running time Fn, there exists positive constant C and N naught such that our running time is positive more than 0 or 0, but less than some constant times Gn for all n that are more than N naught. This is also one of the things that you have to be careful when working with big O is if you're trying to compare 3 or 4 different running times of algorithms, let's say F1N, F2N, and F3N. One common mistake that you might make is you might take n equals 3 and calculate how much time this takes, calculate how much time this takes, and the third function takes. And maybe you'll find that F2 does really, really well, right? That is the running time of this function, let's say, is very, very low. What you may have to be very careful is this 3 may be either below n naught or above n naught. So if it is above n naught, the numbers that you get become the representative numbers. That is, they'll tell you the exact nature of the function. But if this number happens to be below n naught, then this may be misleading, and you may get a wrong idea for which one's fast and which one's slow. The last type of asymptotic notation is the big omega. And what big omega does is it checks for the asymptotic lower bound. That is, it provides the asymptotic lower bound for our input function fn. In other words, what we are looking at is if my input was ideal for the algorithm, how fast can the algorithm run, right? And once again, going back to the insertion sort algorithm, we know that the running time is, this should be n squared plus bn plus c. In ideal case, when the data is already almost sorted, we know that the best case scenario is n. So we say that the running time of insertion sort is big omega of n. So once again, the issue of n naught also arises when calculating big omega. We say that a function's running time is big omega of gn if the function, for the function that exists positive constant c and n naught, such that the function is lower than c times that function for all n more than n naught. So this concludes the asymptotic notations, various asymptotic notations, the big O, the big theta, and the big omega that we just discussed. Now let's look at some examples to clarify our understanding of big omega, big theta, and big O. So remember, the insertion sort algorithm can range from a running time of n to n square. Merge sort always takes a running time of n log n. And big theta gives us the tight bound, big O gives us the upper bound, and big omega gives us the lower bound. So let's look at the first statement. Insertion sort's running time is big omega of n. So big omega is a lower bound, right? And what this statement is saying is that the best case running time or running scenario of insertion sort is big omega of n. So this is true because we know that insertion sort ranges from n to n squared. So insertion sort's running time is big omega of n. This is a true statement. Insertion sort's best case running time is big omega of n. So when we say use this scenario best case, what we mean is best case for the insertion sort. So what is the best case for insertion sort? When the items are already sorted, right? Already sorted. So if the items are already sorted, can we say that the lower bound running time is n? Yes. So insertion sort's best case running time is big omega of n is also true. Insertion sort's running time is big O of n squared. So what we are saying is the big O is the upper bound. So the worst case scenario of insertion sort is, that is upper bound for insertion sort is big O of n squared. This is also true because insertion sort at worst can be up to n squared, right? The next statement is insertion sort's running time is big theta of n squared. So insertion sort has a tight bound, so big theta is tight bound. So what this statement is saying is insertion sort has a tight bound of n squared. In other words, what this means is the running time of insertion sort can be packed between some constant c1 n squared to c2 n squared. Now, this is not true because in the best case scenario, insertion sort's running time may never even be n squared. It may just be n in terms of n, right? So this statement is false. Now, insertion sort's worst case running time is big theta of n squared. So when we say worst case running time, that means this for insertion sort, the worst case running time is reverse sorted data, right? So if the data is reverse sorted, can we say that insertion sort takes a tight bound time of n square? Yes, because if the data is reverse sorted, insertion sort always takes a time around n square, and we can guarantee that the running time is a big theta of n square. Now, merge sort is very easy because merge sort's upper bound, lower bound, and tight bound are all n log n, right? So for that reason, merge sort's running time is big O of n log n, big omega of log n, n log n, and also big theta of n log n.